Hi students, we did not have time in class on Monday, February 11th to look at the solutions to your requested problems 45 and 73. So here is a discussion of solution for problem 45. The problem states that a radioactive nucleus at rest decays into a second nucleus, an electron, and a neutrino. The electron and neutrino are emitted at right angles and have momenta of 9.6 times 10 to the negative 23rd kilogram meter per second and 6.2 times 10 to the negative 23rd kilogram meter per second, respectively. Determine the magnitude and direction of the momentum of the second recoiling nucleus. So this sounds really complicated and like, oh my gosh, we're going to have to look up the mass of an electron and the mass of a neutrino, and wait, neutrinos don't have mass, and something about, this, how do we even know about the, original nucleus and the second nucleus, the daughter nucleus, and all that jazz. But we really just need to pay attention to the details, right? So the detail number one is that the whole thing is at rest before, right? We have the before and after. We need to note that it is an explosion, and so an explosion situation is the reverse of an inelastic collision, which is to say that momentum is conserved. And so momentum is conserved if the momentum of this system is 0 before the collision. Then the momentum of all the pieces after the collision also needs to be 0. So that's our key idea. The momentum of the system is conserved. An explosion is the same thing as an inelastic collision. We just switch the before and after. We start with a collected item moving together, in this case not moving together. We end with separate items that must have a net momentum, a total combined momentum that's the same as the momentum of the collection before the explosion. So the at rest tells us that the momentum before is 0, and then it tells us that the momentum of the electron is 9.6 times 10 to the negative 23rd kilogram meter per second. The momentum of the neutrino is 6.2 times 10 to the negative 23rd kilogram meters per second, and they're at right angles to each other. So it doesn't really matter which direction is which. This can be momentum in the y direction after the collision. This can be momentum in the x direction after the collision. We know the quantity and we know the direction. Purple for y and orange for x. And I know that whatever happened here, the momentum of the I forget which is which, the momentum of the neutrino in the x direction has to balance the momentum of the daughter nucleus in the x direction. This needs to be negative px. These two vectors need to be in balance because the net momentum of the system needs to be 0. And the momentum gained by the electron, so the y component, has to be equal to the momentum gained by the daughter nucleus in the negative y direction. So the purple vectors need to be in balance and the orange vectors need to be in balance because the momentum of the whole thing as a whole has to be 0 both before and after the collision. So now I'm going to say, okay, I can stop worrying about the electron and the neutrino. I'm just looking at my daughter nucleus, piece 1, and I know that it needs to have a momentum in the negative y direction of negative 9.6 times 10 to the negative 23rd kilograms meters per second, and it needs to have a momentum in the x direction in balance with the momentum of the neutrino of 6.2, negative 6.2 times 10 to the negative 23rd kilograms meters per second. And really the negative sign doesn't matter. We could have said that the neutrino and the electron were going in the negative y and x directions, but we've been asked to find the magnitude and direction of the momentum of the recoiling nucleus. So I've got an x component vector of known magnitude and a y component vector of known magnitude. I'm going to recombine them to find the net momentum, which is going to be in the negative x and negative y direction. So now we're back to trigonometry. I have a side of 6.2 times 10 to the negative 23rd and a side of 9.6 times 10 to the negative 23rd. So the magnitude of the momentum is equal to the square root of those squared sums. And of course, these are very small numbers, and we can often make mistakes in entering scientific notation in our calculators incorrectly. But it's nothing we have not done before. It's just weird numbers. So the magnitude of the vector is equal to the sum, the square root of the sum of the squares. Pythagorean theorem, aka Pythagorean theorem. I'm actually going to just cheat a bit and look at the solution. Nah, that's all right. Let's look at how my calculator does scientific notation real quick. Like, y'all have much nicer calculators than me, but this will be like the basics, right? So I want to square 6.2 times 10 to the negative 23. So 6.2, I use my scientific notation. I make sure I'm including the negative sign. Oh, and this calculator, you have to come out of scientific notation and then close parentheses. That gets squared, right? So they're in a very even smaller number. I'm adding then 9.6 times 10 to the negative 23. Again, come out of scientific notation, square it, and then I need to take the square root of the answer. So 1.1428 cha-cha-cha times 10 to the negative 22nd. So my magnitude, 1.143 times 10 to the negative 22 kilogram meter per second. And then I really have included way too many, right? These only have 2 sig figs, so I should be 1.1 times 10 to the negative 22. And then the direction, so maybe I'll go by this angle here, right? So this is theta, if I define it as such. So now I'm going to say that the inverse tangent of my angle, or that my angle is equal to the inverse tangent, right, of opposite. So that would be px over py. Right, so I'm looking at this angle, I'm looking at opposite to this angle. This is the orange x component. I'm looking at adjacent to this angle, opposite over adjacent. So adjacent is the y component. And so again, I'm going to go, showing my calculator function here, or hoping that it's visible on the screen. I'm looking at the inverse tangent. So accessing the trig functions on this calculator is not fun, but inverse tangent of, and again, it's this issue, my opposite is the x component of 6.2 times 10 to the negative 23, and again, I have to come out of scientific notation to close parentheses, divided by, and I don't think that the parentheses around scientific notation are necessary for my calculator, but I prefer to be safe rather than sorry in terms of making sure the computer or the calculator sees that scientifically notated number as a number and not doing something weird with powers of 10. So 9.6 times 10 to the negative 23 is my adjacent side, and close parentheses, and then close parentheses to complete the tangent. So I'm getting an angle of 32.86. I know that I'm in degrees. You can see degrees right there, possibly. Ooh, nope, it's pretty, oh, nuts. I froze a little bit too. But there's a lot of glare, so you can see degrees there. So 32.8. Really, we should have 2 sig figs, so 33 degrees. And this would be 33 degrees, I don't know. This would be 33 degrees from, let's see, this would be clockwise from the negative y-axis. Right, we're just defining random directions because all we knew was that the two subatomic particles were at right angles to each other. I suppose we could measure it from the direction of the electron or something, but this is sufficient for this problem. Please don't hesitate to email me with questions, or even to be prepared to ask some questions on Wednesday at the start of class before the test.